Hello everybody, we are discussing arithmetic building blocks, and in today's class we shall discuss overflow detection in adder and also how to perform BCD arithmetic. So, we shall see BCD adder and subtractor circuit, and also we will have some idea about the underlying theoretical concept, that is tens complement, and we shall also have a look at what would have been the case if we had employed nines complement for BCD subtraction. And during that course we shall also look at the equivalent similar relationship for binary subtraction that can employ ones complement. We had used twos complement subtraction. So, what could have been the case if we had used ones complement subtraction? So, first we discuss the overflow detection. So, for that we again revisit the number representation. So, in this particular case we are looking at 4-bit number representation. So, that 4-bit considers also the sign bit. Okay. So, when we consider sign bit with 4-bit, we remember that in twos complement format we could represent a number from -8 to +7. Okay. We remember that, and how the numbers were there. So, these are the numbers. So, 0 0 0 0 was 0, 0 0 0 1 was 1, 0 0 1 0 was 2. Okay. So, up to 0 0 0 1 1 1. So, this basically behaves like a sign bit, that was 7, and 1 0 0 was -8, 1 0 0 1 was -7, 1 0 1 0 was -6. That way 1 1 1 1 was -1. We remember that, isn't it? So, if we are now looking at the possibility of the overflow, so that occurs when a positive number is added with a positive number and the value of that is more than 7. Okay. So, it goes out of the range. Okay. And a negative number is added with a negative number. So, and the output becomes more than -8, I mean less than -8 from the negative number representation concept. The magnitude is more than 8. So, number is more than -8. Okay. But when we are adding a positive number with negative number, the result, I mean if the positive number and the negative number to begin with are within range. So, of course, the result will be within the range, because one is getting subtracted. So, magnitude will be within the range. Okay. So, we do not have a case of overflow when we are having a positive number added with a negative number. So, positive number added with positive and negative number added with negative, there could be possible cases of overflow. So, if we look at examples, so 0 0 1 0 and 0 0 1 1, if we add them up, simple binary addition. So, 0 1 0 1, sign bit is positive, absolutely no issue, 5 is within the range, there is no overflow. So, whereas when we are adding say 2 with 7, okay, so 0 0 1 0 0 1 1. So, if you add them up, you see 1 0, this is 1 1 1 0, here there is a 0, okay, then there is a carry, then this 1 and 1 0, there is a carry, okay, and finally this is 1 and there is no carry. Of course, there is no carry here. Is it clear? Right, this C3. So, there is no carry. That is what we see, 1 0 0 1. Now, this is, if you look at, actually the meaning is +9, we know addition of 2 and 7. If it had been binary coded, this was not a sign bit, right, but it would have been represented as 1 0 0 1. But we know that this is this is a number representation where the maximum positive number is +7, and 1 0 0 1 is over here, it is -7. So, it is out of range. Okay. So, there is a overflow. Now, we look at the example of negative number with negative number. So, -2 and -3, say let us look at that. So, -2 is 1 1 0, from here you can see this is -2, and -3 is 1 1 0 1, you add them up. So, this is 1, this is 1, 1 1 0, right. There is a carry over here, okay. And then 1 1 1, there is a 1 and there is a carry over here, right, and that carry comes here and we ignore that carry, and this is 1 0 1 1, and we see the result is 1 0 1 1 is minus 5, which is correct, which is a valid number, and the result is also correct, it is within the range. And if we have minus 2 and minus 7, so what we see, minus 2 is 1 1 1 0 and minus 7 is 1 0 0 1, we have already seen that, right. So, if you add them up 1, right, this is 1, this is also 1, 1 1, so there is no carry here 1, so there is basically no carry, you can see no carry. Why I am writing this, that will be clearer later, and this is 1 1 0 and there is a carry. So, this is the carry over here, again we ignore the carry 0 1 1, so what is it? It is plus 7, which is of course not the right thing, okay. So, this is the case of having a overflow, the answer would have been minus 9, but it is minus 9 is out of range, minus 8 is the maximum that we can have, okay. And these are examples of positive with negative, we can see that there will never be a overflow because the magnitude is always within the range, right. Now, how then we can detect if we have a adder fed with these numbers, then how we can detect? We just can develop a simple logic circuit which will take input from this adder, the sum and carry bit that is getting generated, right. If it is a 4-bit addition, S0 to S3 that will get generated, and carry will also be generated, right, and intermediate carry if it is available, C2, C1, C0 will also get generated. So, what we can see, the overflow occurs when, these are the two cases, when the sign bit here A3 prime, okay, is 0, sign bit here is 0 and sign bit here which is S3 is 1. So, this is a case A3 prime, B3 prime and S3. So, this is the case when it occurs. You see in the other cases it will not occur, right. When if S3 is 0, you will see that this will not generate this output to be 1. And the other case when it occurs, the sign bit here is 1 1 and the sign bit that is getting generated S3 is opposite, right. So, these are the cases when A3, B3, these two are 1 and S3 is 0. So, we are taking S3 prime. So, we add them up, then we can get it, right. And if we have access to intermediate carry C2, C3 is the final carry that is getting generated, right. Then we can see that wherever there is overflow, the C3 is the final carry and C2, the carry just before that, C3 and C2, just before that they are if one is 0, another is 1. So, if you take XOR of that, you can get the overflow detected, right. For other cases, you can see this is 1 1 and similarly this is 0 0, you will see that there is no such case that is generating the carry for C2 and C3. So, this is another way just having an XOR gate. So, if you have got access to C3 as well as C2, otherwise A3, B3 those are the input data and S3 is getting generated, you can put them together with a logic relation like this and you can get overflow detected. Is it clear? Right, and if there is overflow, we have to take remedial action. Now, we will look into BCD addition and subtraction. So, before that again we look at how BCD numbers are represented. So, BCD numbers are binary coded decimal, we have seen BCD decoding and other things before. We are already familiar that BCD numbers are from 0 to 9. So, this is the decimal number, decimal representation, you have got digits from 0 to 9, right, and corresponding binary codes are 0 0 0 0 to 1 0 0 1. So, in BCD coding any number more than that is not valid, okay. And if that is for one digit, if you have got a 2-digit decimal number say 53, how do you represent it in BCD? So, 5 we represent as 0 1 0 1, okay, fine, and 3 is represented as 0 0 1 1. So, BCD coded 2-digit decimal number 53 will look like a 4-digit binary number 0101 0011, okay, 0101 0011. If it is a binary coded decimal, the corresponding decimal is 5 and 3. It is a group of 4 you have to take. Okay. So, if we look at some examples, so 10, so 1 and 4 zeros, right, 99 1001 1001, 100 0001, 0 is 0000 and 0 is 00. So, this is the way 12 digits will be required to represent 100. Similarly, if you are looking for 6902, a 4-digit decimal number getting represented. So, 6 will get converted to 0110, 9 is 1001, 0 is 4 zeros and 2 is 0010. So, this is the way you represent binary coded decimal, and we are talking about addition and subtraction of this kind of numbers, this kind of number representation. Okay. So, how do we do that? So, first let us look at some of the theory that goes into the development of the circuit for BCD addition. First of all, we see that the result of BCD addition is valid when the sum is less than or equal to 9, okay, because up to 9 you have got valid BCD representation. So, if you are adding 5, if you are adding 5 decimal which is represented in BCD as 0101 with 2 which is represented as 0010, then we will get 0111. So, that is 7, which is absolutely no issue, right. Similarly, 3 with 6 we get 9, absolutely no issue, but problem occurs when the number sum of these two numbers is more than 9. Okay. For example, over here, so 0100, that is your 4 and this is your 7. Okay. When you add it up 1011, which is as a binary number, 1011, if you look at the weights. So, this is your 8 to 1, 11, that is fine, but 11 is not a valid BCD decimal representation, there is no symbol for that, okay. And we are looking at symbols which is 0 to 9. So, up to 1001 you can have a number presented here, a group of 4 digit. So, this is not a valid BCD, okay. You look at another example, say this is your 9, right, and this is your 8. If you add them up, you get 10001 and there is a carry, okay. So, this is again something which is going out of the range. When you add it up, it is 17. 17 is not what you will get within a decimal representation as a symbol, okay. So, these are the cases when we are having issue, when the number is going more than the result is becoming more than 9, and we can see a solution can be obtained by a simple addition of 6 in each cases, okay. Let us see how it happens. So, this was 1011. So, this result when it is more than 9, you have to develop a logic circuit that will add 0110. So, if you add it up, what will happen? So, this is 1, this is 110 and there is a carry which is added with 1 is 0, there is a carry with 1 0 and this is 1, okay. So, this is now a proper BCD coded representation of the result, and if there is 1, so you put leading zeros which does not alter the value. So, this is 0001, one BCD number, right. So, corresponding decimal is 1, 0001 is 1 and this is another number. So, 0001, 1, 1. So, if you take it to a display device, okay, through this 4 digit which converts to a 7 segment display driver and all. So, the display device will show 1 and 1, which is 11 and which is the correct result. Is it clear? Right. So, similarly, in this case this was 17, if you look at in corresponding binary weighted value, right, and if you add it with 6, right. So, this is 0 1 1 1, that is 7, and this is 1. So, you can check for every such cases it will happen in that manner, right. Whenever the number increase is more than 9, you add 6, you will get the corresponding the correct representation of in the BCD format. Okay. So, this is we will keep in our mind and try to develop the appropriate logic function for this. So, what is that logic? Because it will be part of the circuit, right. You have to develop the corresponding adder, BCD adder. So, we see that for decimal result, I mean when you are doing the representation, when it is remaining between 0 to 9, okay. So, the addition, whether it is required or not, addition of 6 is required or not, if we take this as a output y, okay. So, y will be 0, that time the 0 means no addition is required, no addition of 6 is required. Okay. Now, instead of the result being 0 to 9, if it is 10, 11, 12 and up to 18, it is possible 2 numbers getting added is 9 and 9, that is the maximum. So, in each of these cases this output is 1, because addition of 6 is required. And what are the corresponding representation for at that time? These 10, 11, 12, if you have the adder, the 4 sum bits are S0 to S3 and the carry bit is C3. These are the corresponding representation 0, 1, 0, 1, 0, that is your 10, and 1, 0, 0, 1, 0, that is your 18. Okay. So, there can be with 5 such bits, you can have 32 different possibilities. So, possibilities more than 18, 9, 10, 20, etc., that will never occur if the input digits are BCD, okay, because maximum 9 and 9 can be given as input. So, we do not care. So, those values are do not care, I mean you do not really bother about what will happen if in this case of if 19 is presented. Is it fine? Right. So, this truth table we need to convert to a equation, and we can see that this truth table, if you can just simplify using standard process, algebraic or kernel map or QM algorithm, you can see that a relationship something like this emerges. Okay. So, if you just quickly have a look at, so C3 means, right. So, whenever C3 is there, right, you need to have the y flag, the addition of 6 high, is not it, because that is C3 means the number is 16 or more. S3, S2. So, this is your S3 and S2. So, S3 and S2 means if both of them are there. So, this is the case, these are the cases. Okay. So, S3 stands for 8 and S2 stands for 4. So, 8 plus 4 12. So, 12 and more, right. These are the cases, of course, at that time you are having a value which is high, and S3 S1. So, S3 occurs, that means it is 8 and 1 S1 is also there, that means 2, right. So, you can see all those cases is not there or not there, the number is more than 10. So, these are the cases you can see which is perfectly fits this equation, and otherwise as I said you can do the minimization by standard process, okay, taking the min terms and then minimizing by Boolean algebra or through KM kernel map or QM algorithm, and this is what you get. So, basically you have to realize this combinatorial logic in hardware and then the job is done. Okay. But how the overall circuit will look like, let us see. So, this is how the overall circuit will look like for the adder, okay, BCD adder. So, here what you have got, you have the first adder 7483, a 4-bit adder generating S0 to S3, that what you see, and this is your C3, right. And if this BCD adder takes carry from previous stage, it will take, so that carry will be used here. And this is the logic circuit to generate your whether the 6 will be added or not. So, this is taking C3 this is your C3 getting connected here, this is your C3, right. Then S3 and S2, so S3 and S2 and S3 and S1, okay. So this AND gate S3 S1, this is S3 S2, and finally it is odd. So if it is 1 means 6 need to be added, and if it is 0, that means no addition is required. I mean, no addition required means here in this particular case, since we have to put a adder, so basically 0 is getting added, okay. So this number, the number that was added before, it is now brought forward to the next adder, right, next 4-bit adder, and here, right, the number is, when this is y is high, so 0 1 1 0, A3 is 0, A2 is 1, A1 is 1 and A0 is 0, right. So that what does it mean at that time? Then 0 1 1 0, that is 6 is getting added, and if this is 0, so this will be 0 0 0 and 0, right. So no addition, I mean no number is actually getting added. So the final thing will be the BCD digit, and if there is a carry, right, so that carry will be displayed with leading zeros the way I had shown. Otherwise, if there is another BCD number getting added, like 53 example I had given before, then this carry will be taken there, okay, to the next BCD adder unit, okay. So there it will be given as input. Is it clear? So this is how a 1 unit of BCD adder will act. And we look at one example here. So 49 is getting added with 58, okay. So 0 1 0 0, 1 0 0 1 and 0 1 0 1, 1 0 0. So these are the corresponding, this is represented in BCD, 4 and 9, 5 and 8, and when you add it up, okay, so there is a carry here, it is generated, so the number is more than 9, so 6 is getting added, okay. So this is the corresponding number, that is 7 will be there, and this carry is now getting added with the next numbers 4 and 5, okay. So 4 and 5, so there is corresponding number and 1 is getting added, 1 0 1 0 you get, that again is not a valid BCD, okay. So you add 6 here, so you get 0, okay, and a carry is generated as 1, and then you put the leading zeros, so the result is 107, okay. So if you look at it in decimal, it is also in 107, you can add it up and see. Now BCD subtraction. So to do BCD subtraction, we shall look at what is known as subtraction by tens complement. So we had done subtraction by 2's complement in binary, it is somewhat similar. So what is it done here? So if you consider, you are subtracting a smaller number from a larger number. So two possibilities, smaller from larger, larger from smaller, okay. So say the example is of 7 minus 4. So what we do first, the subtrahend, the way we had done 2's complement, here we shall do 10's complement, okay. So 10's complement is 10 minus the number will give you the tens complement of that, and that is the negative number of, in that sense. So this will give you 6, right. Then you add it up, 7 plus 6, it is 13, right. And if carry is present, the result will be positive. You can see the similarity between 2's complement addition of a negative number, okay. So you ignore the carry, and difference is without the carry, you remove the carry, sorry, 13, so remove the carry, so 3, so the answer is positive. So 7 minus 4 is positive 3, okay. And had it been 4 minus 7, how would have been the case? So we will take 10's complement of 7, which is 10 minus 7 is equal to 3, okay. 4 plus 3 is 7, and when you see there is no carry, so basically 7 means 0 7, right. So carry is absent, means result is negative. Again you can see the similarity with 2's complement subtraction. So now the difference, the result earlier in that case was in 2's complement form if it is negative. So we have to do another 2's complement to get the original, the magnitude of the result in proper binary coded representation, okay. So in this case you will be doing in this case when it is negative, if you want to know the magnitude, so 10 minus 7, 10's complement of 7, so 10 minus 7 is 3, right. So, the answer is negative and the value of it, magnitude of it is 3, so minus 3. Okay. So, this is how you can perform 10's complement subtraction for decimal numbers. And now we come to the representation of the decimal number in BCD and how the circuit will look like. So, to do that, we see that we would require one 10's complement generator here, and if the result is negative, another 10's complement generator here. Okay. If the result is positive, it is not required. Okay. But when you are talking about a hardware, it will be in place, whether you use it or not, that is a separate thing. So, first we look at how to generate 10's complement. Okay. So, the circuit over here you can see can generate 10's complement. How does it do? Okay. So, it is doing it by, in this case, this is your 1 0 1 0 when you are looking for 10's complement. Okay. So, this will be 1. So, this is 1 0 1 0. So, 10 and the number for which you are looking for 10's complement, that will be that you want to subtract. Okay. So, subtraction we know already how to do it using a 4-bit adder. So, this is a bank of XOR gate. So, if it is 1, the inversion thing will be coming here, inverted thing, right. So, that is 1's complement will come, and then this is 1 means this is the carry will be getting added. So, that is giving it the 2's complement, and together when you do it, then you get 1 0 1 0. This is the value you will get the corresponding binary coded decimal part of it in the corresponding negative number of, or the 10's complement of the original decimal number. Okay. And if there is a carry, you have to ignore it, right. Is it clear? And if x is equal to 0, what will happen? The same number will get passed. Okay. The same circuit can, in that case, if you can do the addition also, it is for subtraction, it will be requiring to have this particular value to be 1. Okay. So, this is the 10's complement generator. Now, during the subtraction, how does it work it out? Okay. So, the subtrahend is put here, right, and minuend, the number from which it is getting generated. So, that will be put here. So, we are doing BCD addition. Okay. BCD addition we have already seen before, right. And if BCD addition generates carry, then the result is positive and we do not need to do anything. I mean, we have to just take the result as it is, right. So, if it generates carry, so then this output will be 0. So, this output 0 means here this is 0, right. So, basically you are not doing anything, you are that number is getting passed here, and here the sign you can see that to be positive. Is it fine? And what happens when the number is when this number is this carry out is 0, that means the number is negative, right. So, at that time this will be 1 and we need to take 10's complement of this. So, this is what we, when you do, then you get the 10's complement of it. Is it clear? So, this is one BCD subtractor unit. And to end, we shall have a quick understanding of what is 9's complement and 1's complement, I mean in decimal system and binary system, and how it is useful in subtraction. So, in 9's complement, what we do actually, we subtract the number from 9, not from 10. Okay. So, for the same example of 7 minus 4, 9's complement of 4 is 5, 9 minus 4 5. So, 7 plus 5 is 12. So, if carry is present, the result is positive, and at that time we have to do what we have to do, this carry is also often called sometimes called end around carry. So, this carry would need to be added to get the result. If carry is present, carry need to be added to get the result. So, 2 plus 1 3, that is positive, and because of the presence of the carry it is positive, and the value is 2 plus the carry, that is 3. Okay. And the other case, when 4 is subtracted, 7 is subtracted from 4. So, 9's complement of 7 is 9 minus 7, it is 2. Okay. So, 4 plus 2 is 6, and carry is absent, means result is negative. Okay. Understood? So, here the carry was present, here the 6 there is no carry. Okay. It is 0, I mean that means it is 0. Then the result is in 9's complement, we have to perform another 9's complement to get the magnitude of the negative number that is giving the final result. So, 9's complement of this 6 is 3. So, the answer is minus 3. So, now if you look at 1's complement subtraction for binary numbers. So, this is your 7 and this is your 4. So, 1's complement, we have seen it before, basically it is just inversion of it. Okay. So, 1's complement of this 0 1 0 0 is 1 0 1 1. Okay. You add them up, 1 0 0 1 0, carry is present. So, result is positive, and what you have to do in 2's complement, it was result was just like that. In this case, this carry need to get added the way we had done here. For 9's complement, 1's complement, the carry need to get added. So, 0 0 1 0 added with 1. So, this is 3 and the result is positive. Okay. And larger from smaller. So, this is 4 minus 7 case. So, 0 1 1 1 0 triple 1, 1's complement is 1 triple 0. So, if you add it up 0 1 0 0 with 1 triple 0, you get 1 1 0 0. So, the carry is absent. So, result is negative, and to get the actual difference you have to take 1's complement of that. So, you have to invert this 1 1 0 all the bits. So, 0 0 1 1, so that is 3. So, that is minus 3, that is your answer. So, with this we just look at the summarizing points of this particular class. Overflow in an adder occurs when the result goes out of range. For 4-bit cases it is minus 8 to 7. For 8-bit cases and other cases, you have to have corresponding understanding of the overflow, and the logic relation that we will get will be accordingly take input from the bits which is closer to the, which is designated as sign bit, or carry of the previous one and the current one, I mean which is there in the associated with the sign bits. Okay. And in BCD addition, if the result is more than 1001, then further addition of 6, that is 0110 is required, and BCD adder will require 2 4-bit binary adder and a logic circuit to decide when the 6 is getting added, and BCD subtraction will require 10's complement generator circuit and normal BCD adder. Okay. So, together 2 10's complement generator circuit and 1 BCD subtractor, you can do BCD subtraction. Okay. And 9's complement subtraction will and 1's complement subtraction in decimal and binary respectively, they have got similarity, and we have seen examples how to do that, and we can convert that to circuitry the way you had done for 2's complement and 10's complement. Thank you.